Okay, this is physics. I'm gonna cover some derivatives and trigonometry. So first derivative, if you have a known constant, like the one you see here, you know that's gonna be equal to 0. Then another important one is the power rule, x. I'm gonna write it in this form, x to the power of n. Move that closer. That's gonna equal to n x to the n minus 1. The way I like to think about this one is you grab the n, you bring it down, and then you subtract it by 1 to get that. Then you also have, let me put a line here. E to the exponent of something, that's going to be completely unphased and just going to be e to the x. Then you're also going to have things like d over dx to the natural log of x, which should be 1 over x. Then you can have things like to the sine and cosine. So the derivative of sine is going to equal cosine theta. And then from there, the derivative of cosine theta is going to equal to negative sine theta. This is going to be especially important when you're doing wave functions or oscillations, because you're going to go sine, cosine, negative sine. And I'm going to come back to that. Let me do a few more first. Move this down. So another one is d over dx for the square root of x. That one always seems to trip people up. The way I like to do this is I turn that x to the 1 over 2. And then I use this power rule here. So from there we can take the 1 over 2, bring it down, then subtract it by 1, which that's going to give us 1 over 2x to the power of over 2. That 1 is the same as 2 over 2, so minus 2 over 2, which is going to be negative 1 over 2. Let's see if I can get a different color. It'll be negative 1 over 2. So that gives you 1 over 2x to the negative 1 over 2. You can leave it like that, or you can take it one step further and recognize that that's going to be square root of x underneath a fraction. Cool? And then let's do, I remember using this and having to look it up. So I'm just going to put it down here. I'm not sure if you guys will be using it a lot, but I think it's called the product rule. So it's basically saying you have two functions that are both derivable. You're just going to do one function at a time. So x. So in the first one, you leave one alone, and you do the other one. Then you do plus, and then you do the derivative of the next function and leave the other one alone. Right? So this can look as simple as, we'll say x minus 1 and x squared. That seems pretty easy. So we can leave that x minus 1 by itself for now. And the derivative of that x squared. So we're going to take the 2 down, minus 1, right? So that's going to give us 2 to the x to the power 1. And then from there you plus it to this derivative of this one. This is a constant, so that's going to be 0, and this is 1. Bring that 1 down, minus 1. That's going to give you 1x to the power of 0, which is just 1, minus 0, basically. So it's basically going to be plus 1. Oh, let me leave it. It might help some people see it. X to the power of 0. That's the derivative of this one, or you know that one, times x squared, which this is going to essentially become 1. Cool. So those are some of the main derivatives that I remember using. And then let me get into this. That is not the eraser. There we go. Sine and cosine business. So moving on to trigonometry a little bit. I know we usually do, let me change the color on that. Remember, do we have a triangle? Oh, wait, I can do a shape. That's a nice triangle. We have a triangle like this with a right angle and like a little line here, right? Where this is our theta. This is our 90 degrees angle, right? And we normally use something like so, ka, toa, which means sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. Cool? So what that means is if you come back over here, we have our hypotenuse here. That's always the opposite, the angle opposite to this right angle here. So it's always opposite there. And we have our adjacent, which is opposite to your theta. And then you have, opposite to your theta is opposite, and adjacent is next to your theta. Right? But it's helpful to remember where the units, where SOHCAHTOA comes from. It comes from the unit circle, right? So you have your unit circle. Let's see if I can make that a bigger circle. There we go. Right? And you have your x and y axis running through this running through the circle. I gotta get it at 90 degrees. You have your x, you have your y. Right? Now, if you were to draw a random line here, this angle is going to be your theta, right? And this coordinate up here, this coordinate up here, guess what's that going to be? Beyond being your xy, it's going to be your cosine theta, sine theta, which is your x and y coordinate, right? Oh, don't forget that the formula for this circle is x squared plus y squared is equal to 1, right? So if we're using cosine and sine for x and y, then we get cosine squared, theta plus sine squared theta is equal to 1. And this is a rule that you use sometimes. I don't remember using it too much in this class, but it definitely is useful. And it'll probably show up at least once. Anyway. have our line like that, and we have a right angle here, right? So basically, by saying this is your cosine and this is your sine, that means that this is your x direction, right? Because it's along your x-axis, and this is your y direction, right? And it's saying that this x direction is related to cosine. This y direction is related to sine, right? Because of this formula over here, you know that the hypotenuse is 1. The hypotenuse is going to change. It's not always going to be 1 in your actual math, but for the unit circle, it's always 1. But it is also the slope. So the slope is rise over run. Which, hey, guess what? Rise is y, right? Because you're coming up. Or I guess it would be on this side. Rise over run, which is x. Y over x. Guess what that means? That means y over x is also sine theta over cosine theta. Now, if you come back to your tangent up here, your opposite over adjacent, guess how else you can get this? Tan is equal to sine over cosine, right? Because if, let me move this. If tan is equal to sine over cosine, and sine is equal to opposite over hypotenuse, and cosine is equal to adjacent over hypotenuse, then you get opposite over hypotenuse over adjacent over hypotenuse. You combine those to get opposite times hypotenuse, a times hypotenuse. And guess what? That gets you opposite over adjacent. Ta-da! Now, I hope this has given you a better understanding of trigonometry beyond just cosine, like SOHCAHTOA, because it's kind of helpful to know where that comes from. It comes from the unit circle. Oh, I'm kind of running out of space, huh? But also, yes, I know. Remember that if you have a circle, this line here can be anywhere. It can be anywhere, which is where you get oscillations from. Right? Because they just kind of go round and round and round. Well, let me just kind of go round and round and round. So when you have your wave, right? All this really is this line over here from the unit circle oscillating, or going around the circle. And part of me wants to see if I can look something up like that. Unit equal. Because there's something that could give sometimes. Yeah, see, it's kind of like this one, where it's like going around the circle. Although I want to see if I can find one that moves. So see, these are the different triangles on different areas of the circle. When it's at the top of the oscillation, the line is at the top. So that's a good point. When it's at the top of the isolation, this is going to be 1. And your cosine, your x is going to be 0. Your sine is equal to 1, right? Because that's x and y. Because y is equal to 1, and x is equal to 0 at that point. Should be an x. So that kind of helps you remember where things are. Remember that this angle is measured from this line here. Let me put that in a different color. That's pretty thick, but oh well. Oh. Okay, but it says any of them move. Oh, here it goes. That one's pretty slow, but you get the idea. Whereas your line moves around your circle, you're basically making the wave function that is sine. And here they're using radians instead of ones, which is totally fine. Circle innately uses pies, but yeah. I hope that was helpful. And that's all from me today.